In this segment I'll be introducing you to the algebra tiles and some of their characteristics and how we might go about using them to solve questions, problems, algebra problems. So first off, I'm going to talk about the similarities and differences of the algebra blocks and tiles to the base 10 blocks. So this would be our unit. This is our counting unit, our ones, and this is what we're going to be using as our constant variable. And like our integer tiles, we have to be able to have positive ones and negative ones. And so for our purposes, or for my diagrams and all my segments that I'm going to use, I'm going to be using the same tiles. I'm going to call anything that's a red a negative. So just like if your books are in the red, that means you're losing money. It's in the negative. So all my shapes, any shape that's red, that's going to be the negative version of that shape. Every textbook, every publisher, every set of algebra tiles that you might buy in kits, there is no uniformity to this. They're all different. Sometimes even within a textbook, you'll have them with different colors, and their answer key or their test bank will be a slightly different set of colors than what you have in your textbook even. So it's really imperative that you get together with your students and say, okay, for our class, this color is going to be the positives and this color is going to be the negatives, because every book and every teacher does it differently. So it's really important that you make sure that your students are clear on this. So this is our one tile. It's got a height of 1, it's 1 up, and it's got a width of 1, it's got a width of 1. So it's 1 high and it's 1 across, and therefore its area is a 1. So this is our positive one in the green, and this one would be our negative one in our red. The next tile we want to talk about is this tile, and if you've been working with base 10 blocks, there's an automatic desire for students and teachers as well to say, how many of these does it take to make one of these? And it's important that you take a look and notice that if I took a bunch of these together, and I'm going to try to line them up as close as I can so that I can show this to you, that when I add these together, it doesn't really add up. It's not quite right. Now, in most of the ones you're going to have, it's going to take 5 of these 1 blocks about to make close to an X. So what I want to make sure that you stress is I can't trade in 5 of these 1s for an X, or in my diagram 3 of these 1s for an X. They do not line up. They do not line up for a purpose, and that purpose is that we can call it a variable. We know that it's 1 unit high, but we don't know how far across. So we know it's 1 high, just like these are 1 high, but we don't know how far across it is. And that unknown piece is what makes it called a variable. And that allows us to put whatever number that we want in there and work with it as an unknown, as a variable. So just as we had a positive and negative 1, we have a positive and a negative X tile. It's also 1 high and unknown, and we're going to call that X across. If I take an X tile and I make it X across, and I take that same X tile and I make it X high, that would give me an area that is X by X, which gives me a square shape. Just like 10 times 10 gave me 100. A rod times a rod gave me a flat. Well, it's the exact same kind of pattern, except we don't know that they're called 10s. They're unknown, so we're going to call them X's, and its shape is a square. So we're going to call that the X square shape, and naturally this would be my negative X square shape. Now, different publishers and different companies, different textbooks will represent a half of an X, or a third of an X, or a quarter of an X in many different ways. So what I'm going to do is I'm going to call this a half X. And I've purposely made it so it's exactly 1 high, so that hasn't changed, but it's half across. And it takes 2 of these to make 1 X. So I'm going to call this a 1/2 X tile, and naturally I'm going to need a negative as well, so there's my negative 1/2 X tile. I'm also going to I did the same thing for my thirds. There's my positive 1/3 tile. 3 of these are going to make up an X tile, and so these are going to be my 1/3 tiles, and naturally I'm going to have my negative 1/3 tiles, and I'm going to have my 1/4 x tiles and my negative 1/4 x tiles. So lots of them use circles that are shaded in and negative circles shading in, and it's kind of confusing. I want to just keep everything as rectangles and squares. So this is the blocks that I'm going to use for all of my segments talking about algebra. I think it's important for people to understand something about algebra that lots of people don't get, and I'm going to use an example to show us this. So this question, or this number, is 234. When we talk about it in expanded form, and the reason why it's 234 is because we've got an understanding of place value. The 4s and the 1s, the 3s and the 10s, the 2s and the 100s place value. And where it's located has something to do with its value. We talk often with students about showing expanded forms, and so we could write 234 using this technique. We could also then talk about doing the expanded form in this technique, where we actually show this is the number that I have of a certain value in its place value. So I've got 2 sets of 100 and 3 sets of place value 10 and 4 sets of place value 1. We could also go on to talking, when we get into exponents a little bit, that we could write our exponents instead of as 100, we could call it 100 squared. And when we did work with our base 10 blocks, we know that a 10 rod times a 10 rod gives me a 100 flat. And so that 10 on one side and 10 on the other side gives me a square that has 100 in it. And just a moment ago we talked about doing that again. We said it was x by x high, and so that's going to produce a square, and it's going to be called the x square. If this was a 10 and this was a 10, that would be 10 squared, which would give me my 100 flat. So there's our kind of relationship with that. So in our regular number system, we're talking about place values as a power of 10. I could take that exact same question and write it this way, as far as place values in powers of an unknown variable. So this is 234, this is 2a squared, 3a plus 4. So basically what we're doing here is we're trying to do this kind of idea. So I could expand this one to look like this. I'll put this up on top, and I'll put this one beside this one. So I have place values of 1, my 1's place value. I could write it as a 1, or I could write it as 10 to the power of 0. Any base to the power of 0 is a 1. So if I have 4, I could write it as just a 4, or I could write it a to the 0. That's just a 1, so I would just have 4 times 1, which is 4. If I have 3 times a, I could write a as a to the first, just like 3 times 10 is 10 to the first. And if I have a squares, I have 2 sets of the a squareds. So just as part of my introduction, I wanted to make sure that people understand that the exponents on the a values correspond to certain shapes, and we talked about that with the x squared and the 100 flat, and it also corresponds to its place value. So when we're working with higher algebra skills, we're going to look at algebra being discussion around the place values of our variable, in this case a. Just all part of the introduction that I wanted to make sure that people were aware that those a's actually have meaning, and they correspond to the place values that we use with our base 10 blocks. So whatever kinds of things we did with our base 10 blocks, we should be able to also do with our algebra tiles.